Welcome back. Over the last 4 classes, we worked on strategy and A212, understanding the exam, prelims versus mains, and how to play the clock and the penalty. Today, we finally open the quant section, and we open it at the only sensible place to start, the number system. This is the true foundation of quantitative aptitude. Every single quant question you will ever face, an A212, simplification, averages, ratios, time and work, data interpretation, all of it, an A212, is built on numbers and how they behave. If your understanding of numbers is shaky, every topic on top of it wobbles. If it is rock solid, everything above it becomes faster and easier. And here is the good news. The number system is not about heavy calculation. It is about a small set of clever ideas and shortcuts, and A212, the types of numbers, a handful of divisibility rules, factors and multiples, HCF and LCM, unit digits, and remainders, and A200-200-200s that let you answer questions in your head that look, at first glance, like they need pages of working. Master these tricks and you gain both speed and accuracy, exactly what the exam rewards. So today we lay that foundation properly. We will meet the families of numbers, learn to test divisibility without dividing, understand factors and multiples and their close cousins H, CF and LCM, and finish with two of the most exam favorite tools of all, finding the last digit of a number and finding remainders of enormous divisions. Let us build the foundation of quant, one idea at a time. Here is our path for today. First, the types of numbers. Second, divisibility rules. Third, factors and multiples. Fourth, H, C, F and L, CM. Fifth, the unit digit and cyclicity. And sixth, remainders. Let us dive in. Let us begin at the very beginning with the types of numbers, because the vocabulary here appears constantly and you must be fluent in it. The most basic family is the natural numbers and A12, pi and 12, the counting numbers 1, 2, 3 and so on, and A12, pi and 12. And if you include 0 with them, you get the whole numbers 0, 1, 2, 3 and up. These are the numbers we count with, the ones you have known since childhood. Simple, but the foundation of everything else. Now widen the family, add the negatives, and you get the integers and 80 or 200, whole numbers together with their negative mirrors. So -2, -1, 0, 1, 2, stretching out in both directions. Integers let you go below 0, which matters the moment a question involves loss, decrease, or direction. Notice that the naturals sit neatly inside the integers, and A212. Every natural number is also an integer. Widen once more. A rational number is any number you can write as a fraction, P over Q and A212, one number divided by another and A212, which includes all the integers, all the ordinary fractions, and all the terminating and repeating decimals. And the widest common family, the real numbers, is essentially every number that sits somewhere on the number line, including the irrationals like √2 or pi that no fraction can capture exactly. The key picture to carry away is that these families nest inside one another like boxes within boxes. The naturals sit inside the integers, which sit inside the rationals, which sit inside the reals. Knowing which family a number belongs to, and that they nest this way, is the vocabulary the rest of quant assumes you already have. So the takeaway, numbers come in widening families that nest inside one another, and A212, the naturals and whole numbers we count with, the integers that add 0 and the negatives, the rationals that are any P over Q, and the reals that cover every point on the number line, and A212, and each family sits inside the next, which is the basic vocabulary all of quant builds on. Now our first, genuinely powerful set of shortcuts, the divisibility rules, which let you tell whether one number divides another without ever doing the division. Start with the easy ones. A number is divisible by 2 if its last digit is even and A202, 0, 2, 4, 6 or 8. And a number is divisible by 5 if it ends in 0 or 5. These you can check with a single glance at the final digit, no arithmetic at all. That is the whole spirit of these rules. Read the answer of the number instead of grinding it out. The digit sum rules are the real workhorses. A number is divisible by 3 if the sum of its digits is divisible by 3, and divisible by 9 if the sum of its digits is divisible by 9. Take a big number, add up its digits and A12 4. Add them again if you like, until you get a small number and A12 4, and test that tiny sum instead of the whole giant. For example, 4, 5, 6. 4 plus 5 plus 6 is 15, which is divisible by 3. So 456 is divisible by 3. You just tested a 3-digit number in your head in 1 second. And a slightly fancier one worth knowing, a number is divisible by 11 if the alternating sum of its digits are 8212, add 1, subtract the next, add the next, and so on, and 8212 comes out to 0 or a multiple of 11. There are rules for other numbers too, but 2, 3, 5, 9, and 11 are the ones that appear again and again. The point is not to memorize them as dry facts, but to use them as instant tools. Whenever a question asks whether something divides, or hands you a big number to simplify, these rules let you test divisibility mentally, no long division, saving precious seconds under exam pressure. So the takeaway, a handful of divisibility rules let you test whether a number divides without dividing an A2112, even last digit for 2, ending in 0 or 5 for 5, digit sum for 3 and 9, and the alternating digit sum for 11 and 8012, all checked in your head in a second, which is exactly the kind of speed the exam rewards. Next, 2 ideas that are constantly confused but are genuine opposites, factors and multiples. Get these straight and a lot of quant clicks into place. The factors of a number are the numbers that divide it exactly, leaving no remainder. Take 12. It is divided evenly by 1, 2, 3, 4, 6, and 12, so those are its factors. Notice 2 things. Factors divide into the number and 81, 281. You go inward and 811, and the list is finite. 12 has exactly 6 factors and no more. Factors are the building blocks a number can be broken down into. Multiples are the exact opposite. The multiples of a number are what you get by counting it up an A200-fold, multiplying it by 1, 2, 3, and onward. The multiples of 12 are 12, 24, 36, 48, and so on forever. So multiples go outward, and the list is endless, and 821212. There is no largest multiple. All the contrast in your mind. Factors divide in and are few. Multiples count up and are infinite. Confusing the two is one of the commonest slips in quant, so anchor it now. And tying the two together is the single most useful skill here, prime factorization. Every whole number can be broken down into a product of prime numbers, and 8212. Primes being the numbers like 2, 3, 5, 7 that have no factors except 1 and themselves. 12, for instance, is 2 squared times 3. This prime breakdown is the DNA of a number. Once you have it, all the factors, and as we will see, the H, C, F, and LCM falls straight out of it. So learn to factorize a number into its primes quickly, and 8212. It is the master key to this whole area. So the takeaway, factors are the numbers that divide a number exactly, a short finite list found by going inward, while multiples are what you get counting the number up, an endless list going outward, and 8125. Opposites you must not confuse an 8125 and prime factorization. Breaking a number into its prime building blocks is the master skill from which factors H, C, F, and L, C, M all follow. Building directly on factors and multiples come 2 ideas the exam loves, especially in word problems, the H, C, F, and the LCM. The H, C, F, and 8212, the highest common factor, sometimes called the greatest common divisor, and A212, is the largest number that divides 2 or more numbers exactly. Think of it as the biggest thing they share as a factor, the largest number that goes evenly into all of them. The easy way to find it is prime factorization. Break each number into primes and take the primes they have in common. The mental hook is simple: an 80-112 or HCF answers an 80-120. What is the biggest number that divides both? The LCM N81-2 the lowest common multiple N81-2 is the mirror image, the smallest number that all the given numbers divide into. It is the smallest common multiple they share, the first number that appears on all their multiplication tables at once. Again, prime factorization gives it cleanly. The mental hook N80-12 LCM answers N80-20. What is the smallest number that both divide into? 80-20-20. HCF looks downward to the biggest shared factor. LCM looks upward to the smallest shared multiple. Which one a problem needs is usually the whole battle. So tie each to its plain English question. And there is a beautiful relationship worth memorizing because it turns up as a direct shortcut. For any two numbers, the HCF times the LCM equals the product of the two numbers. So if you know two of those three quantities, you instantly get the third without any extra work. These ideas power a whole class of favorite exam questions and 822 fall bells that ring together, people meeting at a starting point, quantities packed into equal groups, and once you can spot whether a word problem is really asking for the HCF or the LCM. Those questions become quick and mechanical. So the takeaway, the HCF is the biggest number that divides two numbers, and the LCM is the smallest number they both divide into, an 8-2 found cleanly by prime factorization. With the handy check that HCF times LCM equals the product of the two numbers and 8 who to hell. And the real skill is reading a word problem to see whether it is secretly asking for the HCF or the LCM. Now one of the single most popular tricks in all of quant, the kind that lets you answer a monstrous looking question in seconds, finding the unit digit and A200, the last digit and A200 of a large power. Here is the secret that makes it possible. The last digit of the powers of a number repeats in a short, predictable cycle. Watch the powers of 2. 2 to the 1 is 2, ending in 2. 2 squared is 4. 2 cubed is 8. 2 to the 4th is 16, ending in 6. And 2 to the 5th is 32, ending in 2 again. So the last digits run 2, 4, 8, 6, and then repeat an 8, 2, 112 odd 2, 4, 8, 6 over and over. The units digit never wanders. It marches in a fixed loop. Because the cycle here has length 4, the last digit depends only on where the exponent falls within that cycle of 4 and 8 to 112. And you find that by taking the power modulo 4. That is, the remainder when you divide the exponent by 4. Most digits cycle in a length of 4, some in 1 or 2, but the method is always the same. Identify the cycle, then reduce the giant exponent down to its position in that cycle. You never compute the huge power itself and A212. You only need to know where in the loop it lands. Let us make it concrete. What is the unit digit of 2 raised to the 30th power? We do not compute 2 to the 30th and 8 to 12, a 10-digit monster. We just take 30 modulo 4, which is 2, meaning the 30th power sits at the second position in the cycle 2, 4, 8, 6, and 84 2, and the second position is 4. So the unit digit of 2 to the 30th is 4, found in seconds with no calculation. That is the power of cyclicity. An impossible-looking question collapses into a tiny remainder calculation. Learn the cycles of the common digits, and this becomes a reflex. So the takeaway, the last digit of a power repeats in a short cycle, and A212, the powers of 2 end in 2, 4, 8, 6 on a loop of length 4 and 80i 2 half. So to find the unit digit of an enormous power you never compute it, you just take the exponent modulo the cycle length to see where it lands, turning a monstrous question into a 1-second remainder. Our last foundation stone is closely related to that last digit trick, and it is another exam favorite, remainders. start with the exact statement of what division really does. Any division can be written as the dividend equals the divisor times the quotient plus the remainder. In other words, when you divide, you split the number into a whole number quotient and a leftover remainder and a to 112. And that equation is the precise definition you can always fall back on. Two facts anchor everything. First, the remainder is always smaller than the divisor and 8212. If it were as big as the divisor, you could divide once more, so what is left over is strictly less. Second, a concrete example to lock it in, 17 divided by 5 is 3 remainder 2, because 17 equals 5 times 3 plus 2. That leftover 2 is smaller than the divisor 5, exactly as the rule promises. Keep both in mind, in A212, the definition, and the fact that the remainder never reaches the divisor. And here is the payoff that connects to the previous slide. Remainders, just like unit digits, repeat in cycles. When you take the powers of a number and look at their remainders on division by some fixed number, those remainders loop in a predictable pattern and A202. So the very same modulo trick that found unit digits also cracks questions asking for the remainder of a gigantic division. You reduce the huge calculation to a small, repeating cycle and read off the answer. This is why remainders and cyclicity are taught together. They are two faces of the same powerful idea that big, scary calculations often hide a small, repeating pattern you can exploit. So the takeaway, every division splits a number as divisor times quotient plus a remainder. And that remainder is always smaller than the divisor and 8212. And, exactly like unit digits, remainders repeat in cycles. So the same modulo trick reduces a gigantic division to a small repeating pattern and hands you the leftover in seconds. Let us gather today and the T99 ask ideas into a single toolkit so you can see how few and how connected these tools really are. First, know the number families and the divisibility shortcuts. Be fluent in naturals, integers, rationals, and reals, and be able to test divisibility by 2, 3, 5, 9, and 11 at a glance. This is the everyday vocabulary and the fast mental check that speeds up every other calculation you do. Second, factorize into primes and A212, and then HCF, LCM, and the full list of factors all follow. Prime factorization is the hub of this whole area. Break a number into its prime building blocks and you can read off its factors. And the moment you have two numbers in prime form, their HCF and LCM drop straight out. One skill, many payoffs. And third, use cycles and modulo for the last digit and for remainders. Whenever a question hands you an enormous power or a gigantic division, do not compute it an 8 to 101. Find the repeating cycle and take the exponent or the number modulo its length. Notice how small this toolkit is. Number sense, prime factorization, and the modulo cycle trick. 3 ideas, and between them, they turn slow, frightening arithmetic into quick, confident mental work. That is the whole promise of the number system and 84 packs, not heavy calculation, but a handful of sharp tools used well. So the takeaway, your number system toolkit is small but powerful, and 80-ID-12. Know the number families and divisibility shortcuts for fast mental checks. Factorize into primes, so factors. HCF and LCM all follow from one skill. And use cycles and modulo for unit digits and remainders, and A212, 3 connected ideas that turn slow arithmetic into quick mental work. Now let us see how you actually deploy this toolkit when a real question is in front of you, because knowing the tools and using them well are 2 different things. Step 1. Read the question and pin down what is actually being asked. Number system questions are often dressed up and A212, a story about bells or boxes or a huge power and A212, and your first job is to strip away the wrapping and name the real request. Is it asking whether something divides for the biggest shared factor, for a last digit? The right first move is always to translate the words into the underlying number system question. Step 2. Reach for the matching tool. Once you have named the request, the tool is usually obvious. 8-20-20. What divides both and 8-20-21 means HCF and 8-20-20. When do they coincide again? 8-20-20 means LCM and 8-20-20. The last digit of a big power ain't 8-20-20 means cyclicity, and 8-20-20, the remainder of a huge division in 8-20, means the modulo trick. This matching an 8-tool POW, question type to tool, an 8-tool POW is the heart of solving quickly, and it is exactly what practice trains into a reflex. Step 3. Apply the tool and then sanity check the answer against the numbers. Do the quick mental work and 8 हुआ सवाल, the digit sum, the prime factorization, the modulo and 8 हुआ सवाल, and then pause for a half second to ask whether the answer is reasonable. Is the remainder smaller than the divisor? Is the unit digit actually a single digit? Does the HCF really divide both numbers? That tiny check catches slips before they cost you a mark. Read, pick the tool, apply, check, and 86 to 12. Run that calm 4-beat process, and even intimidating number questions become routine. So the takeaway, put the toolkit to work with a calm process and 82 fall, read the question and name what is really being asked under the story, reach for the matching tool, whether that is H, CF, LCM, cyclicity, or the modulo trick. Then apply it and sanity check the answer against the numbers and 825. And with practice, that red pick apply check routine turns even intimidating questions into quick, reliable work. Let us gather the whole class in one breath. Types of numbers and 821, 12 curve, naturals, integers, rationals, and reals, each family nesting inside the next. Divisibility rules and 825, test 2, 3, 5, 9, and 11 in your head with no long division. Factors are multiples and 821, 12. Factors divide in and off finite. Multiples count up and never end. Each CF and L, CM and A, T112V. The biggest shared factor and the smallest shared multiple, with 8CF times LCM equal to the product. Unit digit and 85 to 12. The last digit cycles, so take the power modulo the cycle length. Remainders and 85 to 12. Divisor times quotient plus remainder, and remainder cycle 2. Next class and 8 to 1, 12V. Simplification and approximation, the speed skill of quant. One idea at a time. That is the number system.